I made it. Let the record state, I actually made it here on time. I tell you, sometimes we usually don't have traffic here, but man, it can get nuts. So, share screen. All right. I guess. Go. All right. So I do have to go around and check everyone's thing. So wait a second. I'm not clear. Huh. That is a little strange.
What, for yours?
Yeah.
Do you know symptoms still?
Well, I assure you guys, I don't have any symptoms.
Weird.
But that's not a repetition. Thank you.
It's a mobile glitch or something?
I sure hope so.
Don't worry.
Unless, oh, I know, I'm not. Unless the app is smarter than I am. We'll figure that out. So, all right. I know I'm just doing my job. I hate checking that stuff in the beginning of class, in case you're ever wondering. It's important. But so, anybody have questions about anything before we start? So we're actually a little ahead of schedule, believe it or not. I think we're gonna end class today with time to spare. So actually I prepared a bit of a problem session. So what I did is I went over the homework, looked through the sections homework and saw where people are having issues. So I'm prepped to whatever time we have left at the end to go over some problems, at least on the homework. So.
Do you have a test date yet?
I guess next Wednesday. Yeah. So which is good because we'll finish the material today. I like there to be a week of, I call it sinking in period, you know, like learn the stuff and then you wait a week and just like, you know, so it just kind of churns through your mind and gets sorted out. So I've met that. So yes, score one for Ferguson. Or at least I should by the end of the day. Anybody have any other questions? Okay, so where we left off, so we're talking about limiting reagents and we're going to theoretical yield. That is how much you could possibly get out of a chemical reaction. And talking a little bit about chemistry and society. And we're talking about, to have that graph, a Malthusian catastrophe. Yeah. We had something happen around the year 1900 that our population has doubled in about 100 years. Doubled twice, I should say, doubled twice in 100 years. So that's pretty fast. You know, if you look at population, especially a population as large as the human race. I mean, we have a pretty sizable population, 7-ish billion people. I mean, like for ants, it might be nothing, but for mammals like us, that's a pretty large population. So something happened around the year 1900. And I mean, this is my own opinion. The two things, actually, well, someone had said it better than I did, is So over here, someone said industrialization of agriculture. That's better than my answer. But I think it's I'll go with that, the industrialization of agriculture, especially nitrogen fertilizers, which I'll get to. And also invention of antibiotics. That's my other opinion. Because more people, if you look at why people die today, number one reason is heart disease. Number two reason is cancer. So slow death. And people our age, the number one is accidents. So that's what kills people our age. So infectious disease tends not to. Whereas if you look before the invention of antibiotics, what killed people? Pneumonia, septicemia, those type of things. Tuberculosis, that was the big killers. So they still do kill people today, but I mean, even though last year, we lost 600,000 Americans to COVID, but I mean, worldwide, we're still losing more people to, even though it's infectious disease, we're still losing more people to heart disease and cancer. So even in a pandemic year. So, and so already mentioned antibiotics, but what about food production? Well, if you looked before the year 1900, you're like, so what do you guys want to do? And like, I can look at your majors. I mean, everyone here is going to be in a STEM field, right? Or flirting with a STEM field of sorts. And if I were to ask the general population what you want to do when you grow up or whatever, I don't know if I'm growing up, heck, but like 50% of people would say food production. You'd be farmers, you'd be sheep herders, you'd be goat herders, something that dealt directly with generating food. Not really, because, well, you're not generating food, but you're serving that. So that would be an artisan class. So then the next highest would be artisan class. So things like the restaurant and the butcher, the baker, the candlestick maker, kind of thing. So that would be the artisan class, and carpenters and blacksmith and that kind of stuff. There'd be very few soldiers, very few aristocrats, kind of thing. And of course, if you look at today, what percentage of the population is geared towards food production? It's around 5%. So 5% of our population, so 1 in 20, from 1 in 2 to 1 in 20. And so what does that mean about to work and to be human in this day and age? It means you go to meetings and sit in front of a computer, right? That's what we do. We have a service economy, and that's what allows us to do that, though, is the fact if we didn't have our agriculture mechanized, we would have to work for food. And we wouldn't have a population as big as we have.
Is it for America that this percentage?
Worldwide, I think it's even a little less for America. I think it might be as low as 3%. So, so plants, which you can learn in future classes. So plants have macronutrients just like humans. Our macronutrients are carbs, fats, and proteins. That's what we need in huge quantities. Plants have macronutrients. They have nitrogen, phosphorus, and potassium. So those are the big things that they need. And specifically, what we found out was that plants need quite a bit of nitrogen, so nitrogen fertilizers. And around the year 1900, the population was around 2 billion. And one of the reasons why the population was so big was because they were mining nitrates from Chile. So there was lots of nitrates being mined in Chile, and also guano, but guano is really more scarce than nitrates. They're using nitrates as fertilizers. And what nitrates do, they make the root systems of crops. There's a lot of roots, and they're big and thick, and a lot of like, I think they're nodes or nodules, or nodules, I think that's what they're called. So you have lots of those in crops. So when you put nitrate fertilizers on crops, it's like steroids. They grow fast, they grow huge, and they produce lots and lots of whatever it is they're making, fruit, corn, whatever it is you're growing. And of course, you need potassium, you need phosphorus. We still mine those, but the big one is nitrogen. And so around the year 1900, we're mining our nitrates. And so it's a mining operation, and our population is starting to explode. And the world's leaders are like, okay, we're headed towards a problem because mining is not very sustainable. It's sustainable now, but it's not going to be sustainable in the future. We need to find a way to make nitrogen from something other than mining it. So we tried different things. So here in the United States, well, actually with Canada, one of the ways you get nitrates is by lightning bolts. So you can naturally nitrate the soil by electric discharge from thunderstorms. So we actually, up in Canada, near Niagara Falls, with all the hydroelectric, they were doing electronic discharge, lightning bolts, and making cyanide, basically, from the lightning bolts. And then taking the cyanide and turning it to fertilizer. But there were two people, maybe you've heard of, I don't know if you've heard of the Haber process, or I guess Aber is the proper way to say it in German. Aber process. And so that's what the process is used to make ammonia. And it's, specifically this one here. I'm also talking about this because the next problem has nothing to, we make ammonia, the next problem, but this is actually how we make ammonia. And ammonia is important because you can take ammonia and burn it to form nitrogen oxides, mix that with water to form nitrates. And then that becomes fertilizer. So basically you make nitric acid and then you react it. The more common fertilizers are ammonium nitrate. So ammonium sulfate is also used in other countries. So in China, they use ammonium carbonate. That's also known as smelling salts. Have you ever seen kung fu movies when they put the smelling salts and people wake up or whatever? That's ammonium carbonate. They do that in China. We don't use that too much in the United States. And urea. Urea is the other one that we use quite a bit in the States. And we also know we generate that automatically. Our animals make that as well. So, but we can make it synthetically. And so Haber, he found a way to make ammonia using osmium. And osmium is even more rare than gold. So that's not a very sustainable thing. Then there was a guy, I personally like this person more, Carl Bosch. So he's not an academic, so we don't call it the sometimes Haber-Bosch process or Aber-Bosch process, sometimes just the Aber process. But Carl Bosch figured out that he also figured out how to do high pressure systems with hydrogen and nitrogen. But he figured out that if you took iron ore from Sweden and you heated it up for 8 hours in the presence of hydrogen, it made a catalyst that works for ammonia production. And how he figured that out, he just tried a bunch. It seems like a random thing, right? So
Only from Sweden.
Only from Sweden. And so the reason why Swedish ore worked, we found this out in the 1970s of all times. 1970s, Swedish ore has impurities of aluminum oxide and potassium. The aluminum oxide restructures the surface, puts the atoms in a specific way, and specifically the 111 surface, if you're wondering. Iron tends to be the 110 surface. That's something you can learn later on. So the surface restructured, and then potassium was a promoter. So it actually, we can talk about more with quantum mechanics. It changed the orbital, the energies. It split them. So nitrogen's was here, then it split here, lower energy, and then it was easier to break the nitrogen triple bond. So, okay, so there are a couple of political things that happened because of the Haber-Bosch process. I'll speak in English now. So Haber-Bosch process. So of course, in the a little after the 1900s, so around 1920, I guess I'm bad with my history. So of course, something happened. It was World War I. So, and people thought World War I was going to be the easiest war ever. At the time, the British were the strong navy, the strongest naval force in the world. They said, hey, look, this is what we're going to do. We're going to create a blockade. We're going to prevent nitrates coming from Chile going to Germany. And nitrates are also used for explosives. So they're not going to have any explosives. They're not going to have any fertilizer. They're running out of food. They're running out of bombs. War's going to be over. No big deal. Of course, Germany was making their own nitrates. And so I said nitrates make explosives. So Does anybody know what TNT stands for? Trinitrotoluene. So, and how do you make trinitrotoluene? You mix nitric acid with toluene. You make trinitrotoluene. Does anybody know what dynamite is made of? Nitroglycerin. How do you make nitroglycerin? You take nitric acid and you mix it with glycerin. You ever read or seen the movie Fight Club? That's what they do. And so,
With the soap.
yep, because fats are triglycerides. You have a glycerin left over with the saponification process.
Okay.
So that's where you get our glycerin from. And so another side story. So sorry for all the history, but so the person that figured out dynamite was a guy by the name of Nobel. Oh, if you've ever heard that name before. He figured out that if you took nitroglycerin is shock sensitive. Like if I had a vial of nitroglycerin and like this, it would explode. Very shock sensitive. So if you take nitroglycerin and you mix it with clay, diatomaceous earth specifically, but clay, and then you put like a blasting cap on it, something like magnesium or something that provides activation energy, you get a really stable explosive that only blows up when you light it. So, and then of course, dynamite became the explosive of choice. Before it was gunpowder. So, but dynamite is much more destructive than gunpowder. And of course, they were using it to blow up mountains to make railroads, but they also use it in warfare. And Nobel, he was called the Doctor of Death because he discovered dynamite and he made lots and lots of money selling dynamite. And he's like, you know what? This is a bad thing to leave behind as my legacy. So what did he do? He was Swedish and he hired a think tank. He said, guys, I do not want to be remembered as the Doctor of Death. How do I prevent that? And the think tank said, what you need to do, you take a big pool of money and create a trust fund. And also then create a panel of people, and they have to go through and think who in the world this year has done something to promote peace. And the hippies, like the bleeding heart hippies of Europe at the time, were the Norwegians. So they said, you know what, have Norway decided because they're the bleeding heart hippies, and then now your name will be associated with peace and not death. And so hence we have the Nobel Peace Prize. Of course, they expanded that to include chemistry, physics, physiology, literature, and economics. So we actually have 6 Nobel Prizes. The peace one is decided through Norway. The other 5 are decided through Sweden. And then it's presented by the King of Sweden as well. So that's, of course, Nobel has carried on his legacy. He's not remembered as Doctor of Death. Yeah.
Do they still hand out Nobel Prizes for like figuring out how to make bombs or nuclear bombs and stuff still? Or
well, the nuclear science for sure. So you had, and some of it also was very sexist in origin. So, forget about who discovered radioactivity, but yes, they've done it for radioactivity. Marie Curie got 2 Nobel Prizes and her daughter got 1. And those were surrounding radioactivity. It wasn't necessarily nuclear weapons. It probably wouldn't.
Did Einstein get one?
Yes, but for the photoelectric effect, not for relativity.
And what about what's some of the capillary effect you discovered?
I don't know about that.
The water?
I don't know. I have no idea. I'm sure Google could find out, but we'll look for that later. So, okay, so going back to ammonia though, and also Sweden, talking about politics, right? So Germany had the ability, I guess was it Prussia at the time? I'm not sure. No, I guess it admitted Prussia. So Germany had the ability to make their own explosives. So that's one of the reasons why World War I went on for so long, because they had the ability to make their explosives and feed their population and not need Chilean nitrates. And then World War II happened. And if you know your history, Sweden was neutral during World War II. So the reason why Sweden was neutral during World War II is because they had a pact with Hitler. And Hitler wanted to invade Sweden. His advisors were like, this is a bad idea. This is the only place we know of that we can get the catalyst to make ammonia. We don't have ammonia, we don't have explosives, we don't have crops, we starve, we die, we have no bombs. So Hitler negotiated peace such that Sweden would supply Germany with the ore. So Sweden was actually, they were neutral. They were neutral. Maybe you could argue on the side of the Nazis, but no, hey. But also, well, Germany at the time and Germany still is very advanced in science, second only maybe to the United States. So Germany also, they've developed a way to make synthetic fuels. So using the same catalyst, it doesn't work as well. Ammonia catalyst, it works for like 10-ish years. But you can do another process called the Fischer-Tropsch process, where you can make synthetic fuels. And the catalyst only lasts like on the order of 2 or 3 months before you have to replace it. But Hitler figured out how to make alternative fuels. And they use it in their tanks, for instance. So their Tiger tanks and whatnot. And so it was a great fuel. I mean, it still is a great fuel. So versus making synthetic fuels versus petroleum-based fuels. They burn cleaner and they're clear. So they're actually like petroleum fuels, like you've seen gasoline, looks like apple juice. It's from the aromatics. It's the, like, well, I shouldn't say impurities, but it looks, like I said, it looks brown. It's like apple juice. Synthetic fuel is clear and it burns more cleanly. So miners and tank operators loved it because it wasn't smoky. But another political thing, go to the 1970s, you have the nation of South Africa. At the time, there was this systematic racism called apartheid, where you had the separation of whites and blacks. Of course, race is stupid anyways. It's a human construct that has no biology associated with it. But the world didn't like this. It said, all right, South Africa, you're being bad. No more oil for you. South Africa goes, we got coal, we got natural gas. We know our history. We can make alternative fuels. So South Africa actually is running off of alternative fuel. They still are. There's a company called Sasol that generates all their fuel. So we actually could go to alternative fuels if we wanted to, but we're just too lazy. So anyways, one of the points I'm trying to say is science is political. So science is political. And it can make or break countries. I mean, so Sweden would have been pretty bombed if it wasn't for the fact they had the resource that the Third Reich needed. And it can change things, like apartheid lasted longer because of Nazi technology, actually. So, and actually right now we've improved it. So we have micro reactors now, and there's some companies that are looking at alternative fuels. So the SAS, the Royal Air Force, or what do they call it, whatever it is in England, they went ahead and said that they use synthetic fuels for their jets. We haven't said that in the United States. I don't know what we use. I know we use sulfur hexafluoride, but whatever we put in our jet fuel is top secret for whatever reason. But the Royal Air Force, so I guess RAF, the Royal Air Force, they use synthetic fuels. But that's where we're also going in the future. I mentioned that also, how it all relates back to this. We might face a Malthusian catastrophe, not in terms of food, but other resources, fuel, so certain materials like rare earths. So that's another thing that might happen. And also, even today, you can see some of the bigger sources of untapped sources of rare earths are Afghanistan and North Korea. China has quite a bit. The United States has quite a bit. There's some on the bottom. There's quite a bit in the bottom of the ocean. But Afghanistan and North Korea have quite a bit of reserves of rare earths. So as you can see, they are contentious spots too. So we'll see. We'll see where that goes. But that's why we need this reaction, because it's where we get our food. And we actually get our food also from fossil fuels. We get the hydrogen we get from natural gas. So, I mean, I know it would be tough if we never could fly a plane or drive a car again. But, you know, take away my frosted flakes with my corn oil, my whatever high fructose corn syrup, that's a problem. Okay, so let's go back to some we call it some calculations here. So this is not how we make ammonia. So I think I told you I'm a very practical chemist. We don't make ammonia this way. We can make ammonia from air for nitrogen. We take natural gas, we react it with water in a process called steam reformation to get hydrogen. And then we react it over iron with impurities of aluminum and potassium heated in the presence of hydrogen for at least 8 hours. And then we get ammonia coming off the back end. So that's how we make ammonia. So we don't make ammonia this way, but we're going to go ahead and this is, I guess, academia has an imaginary part to it too. So we'll just imagine we do it this way. So ammonia can be synthesized by this reaction. 2 nitrogen monoxides plus 5 hydrogens makes 2 ammonias and 2 waters. Starting with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen, what is the theoretical yield of ammonia in grams? So meaning we need to figure out how much we can make of ammonia in this. So to do this problem, before when we were looking at the previous problem, looking at algae, there was tons of water. The limiting reagent was carbon dioxide. And when you're driving your car, it's not oxygen, it's the fuel is your limiting reagent, right? So now we don't know what the limiting reagent is, so we have to figure it out. So we start with 86.3 grams of nitrogen monoxide, and we just have to go across and see how much we make each time. So let's see here, mole NO, and is that 30 grams, 14 plus 16? Yes. 30 grams NO. And then next step is 2 moles ammonia to 2 moles NO. And then 17 grams ammonia to mole ammonia. And you have to do the same thing for the hydrogen. So 25.6 grams hydrogen, mole hydrogen to 2 grams hydrogen. And this is 2 mole ammonia to 5 mole hydrogen, 17 grams ammonia to mole.
Where are you getting 17 grams?
So nitrogen.
Mole?
Nitrogen is 14.01. 7. Hydrogen is 1.008. It's going to be 17 point, so 3 times 0.034. I guess you don't know the last digit. So it'd be 17.03 grams per mole.
17 is fine.
Yeah. So, yeah, and I just have that part of the periodic table memorized. So you don't have to memorize it. So I'm getting the 2 to 2 here, and then the 5 to 2 there. So how are we doing? So does everyone understand how I've set up this dimensional analysis so far? Any questions? Okay. I know the textbook, they stop at moles, but I like to do it all. Okay. Let me do my calculator. 86.3.
So already looking at it, hydrogen's the limiting reagent, right?
I don't think it is. I think it's actually nitrogen monoxide. We'll find out. 48.9 grams ammonia. Ooh, and I could buy Ray-Ban glasses. All right, I like the ads on the free apps, huh? 25.6 divided by 2. Because 25.6 is going to be 12 moles. And actually, that's going to be hard to say. I don't know which one it's going to be. We'll find out. Divided by 2. Oh, times 2 divided by 5 times 17. This is 87.04. Oops. So you get two answers. We get 48.9 grams of ammonia if we react all the nitrogen monoxide, and we get 87 grams of ammonia if we react all the hydrogen. And you say, I'm a very positive person. I believe in forward thought, and I'm going to say 87 grams. No, you can't do that. You have to pick the lowest one. So you are limited by the lowest one. And as such, you pick 48.9 grams of ammonia as your answer. So recap with this one. We have this balanced chemical reaction. We're given 86.3 grams of one reactant, nitrogen monoxide, 25.6 grams of hydrogen, another reactant. And we want to figure out what's the theoretical yield of a product, in this case, ammonia, in mass. So asking for mass. And so the way we do this is we set up two separate dimensional analyses, each starting with the respective reactants. And we find out, so that, well, if we go over the dimensional analysis, convert from mass to moles, then you convert from the reactant to the product, and then back to the mass of the product. So it all cancels out. And for nitrogen monoxide, you get 48.9 grams. For hydrogen, you get 87 grams. And so you pick the lowest one because the nitrogen monoxide is going to run out first. Just like the Happy Meals, right? If you have 10 fries and 1,000 toys, you can only make 10 Happy Meals because you're limited by the smaller amounts. So questions with this one? All right, so here is the next one. 100 grams of oxygen and 100 grams of hydrogen react. How much water is going to form? I'll go and give you a few hints. Hydrogen is 2 grams per mole. Oxygen is 32 grams per mole. So let's try this out. Is anyone stuck and has no idea where to start? Oh, and I should give the reaction. Okay. That's the chemical reaction. Actually, that was one of the homework problems that people had a hard time doing, is going from words to chemical reaction. It was the iron rusting with oxygen. Actually, that was the problem that people had a hard time with. In case you guys are wondering, I am tracking you and your homework. But I know that there's still another week.
The test is next week, right?
Yes.
Is it time?
I put 3 hours. If you run out of time, let me know. I've only had one person come close to running out of time. And that was because the test happened and there was a thunderstorm, or there was a rainstorm, and like the rain was so heavy, it knocked out the student's internet and then connect later.
So you start it.
You have to, when you start, you have to sit through it. You can't come back to it.
But you can start it like whenever you want.
Yes. Let's say you start it and then, hailstorm comes, knocks out your power, and then the time runs out. Just let me know and I'll reset it. So if something happens, it's not a big deal. You don't have to worry about stuff. I'm not the stickler who says, no, you fail. Too bad for the weather. I got to work on my evil laugh. I don't know. Not too crazy. The pandemic has been changing that. Raise your hand if you need help. Zoomers, you doing all right? Can you hear me? I didn't check to see if you guys are connected at all.
Yeah, we can hear.
There is your next extremely heavy hint. If you're stuck. All right, I have just been approved to come to campus. Okay. Let's see what's happened in the meantime. So how many people think A? Show of hands, A. How many people think B? How many think C? How many think D? So I've had 3 students go for B, and that is in fact the right answer, but everyone else has not been playing. So tell me the feedback, guys. Where are you stuck? So if you do this, this is 900 grams. This is 112.5 grams. You pick the smaller one. So feedback is telling me you guys are getting stuck on something. Where are you getting stuck? No one wants to tell me. You just needed more time to do the calculation, or are you getting?
You just like go through it.
Okay, you mean like explain each and every step?
Yeah.
Okay, as you wish. So it's linear reagent problem, and we have 2 reactants, and we have to figure out which one's going to yield the smallest amount of products. Okay, so start with hydrogen, 100 grams of hydrogen, and hydrogen, if you look at the periodic table, so if you look at hydrogen, its molecular atomic mass is 1.008, And I know it should be 2.016, but I'm just putting 2. So a mole of hydrogen is 2 grams of hydrogen. So does everyone understand this step, where this step comes from? Now, if you look at the balanced chemical reaction, so for every 2 moles of hydrogen, there's 2 moles of water. So this step right here is from the balanced chemical equation there. Does everyone get that step? And please, it's okay if you don't. You want to have your oh shucks moments now in class, then when you're taking the test, and then you have the oh shucks moment. It's better to have the oh shucks moment right now. I know I'm doing the Sesame Street swearing with that too. You can replace as you want. And then the last step is, and if you look at the units, so backtracking the units, right? Grams goes away, we have moles hydrogen. Moles hydrogen goes away, we have moles water. Now we got to convert moles of water back into mass of water. And you do that by the molecular weight of water being 18. And then doing so, you get 900 grams. So 100 divided by 2 is 50 times 1. So 50 times 18 is 900. Yes?
I did it a different way.
Okay, did it work?
It worked, but I was wondering if it would be easier, like people saw it differently.
Let me see.
So I found the moles for O2, and then I multiplied, and I found the moles for H2, and I put that here, and I multiplied that by the grams.
Yeah, that'll work. But that's also individual step by step.
Yeah.
Yeah.
I didn't do that analysis.
Yeah. If you don't mind, I'm gonna
Keep doing that way.
keep the analysis because it's clean and neat.
Okay.
That's a perfectly acceptable way to do it.
All right.
So one thing I know, one of the lessons I took from 3 classes ago, if I talk about more one way to solve a problem, it upset the students. So yeah. I'm trying to, not to do that. I'm trying to keep the students from being upset. So, okay. Does that make sense for the red line here, the top line? So you do the same thing for the oxygen, except a mole of oxygen is 32 grams. So 2 times 16 is 32. And there's a 2 mole to 1 mole ratio of water to oxygen versus 2 to 2. And if you're wondering, when I multiply this in my calculator, I just skip this step because they cancel. So, and doing so, you get 112.5. Is this making more sense? I'm getting some people nodding their head. Come on, guys, feedback. I want to teach you. I want to do a good job. Are you getting this? Is this yes or no, or is this?
On the third step, so the 2 mole H2O, that's because with 1 O2 you can make an H2O. That ratio.
Wait, this.
On the bottom.
This one here.
Yes.
Because for every 1 part of O2, you make 2 H2Os.
Okay.
Yes. Other questions? All right. Am I okay to consider this matter done then and move on, or do you need further clarification? Raise your hand if you do not want me to move on. Okay. You guys, what about Zoomers? You okay? Questions, anyone? Okay. Your silence will be consent then. Okay. So next problem here, we can obtain titanium metal from its oxide according to the following balance equation. Titanium dioxide plus 2 carbons makes titanium solid and 2 carbon monoxides. So first of all, a couple things about this chemical reaction. So this is, in fact, how we get metal from ore. So the book actually got something right for a change. This is reduction. It's called reduction of carbon by ore to get metal. So a couple things: titanium dioxide, TiO2. This is also known as rutile. So it's white. We use it in paint. It's the white lines in robes. We also use it for sunscreens. So titanium dioxide is very common, and we use it commonly. And then we'll learn about reduction actually next chapter. But the way that we get most metals is we reduce it with carbon. So this is proper, although the product is going to be liquid. It's usually liquid metal. It's not solid metal. And it's going to be carbon monoxide or carbon dioxide. And so the biggest example of doing this is actually for, maybe you've heard of a blast furnace before. A blast furnace works, you put in iron oxide, or really any ore. You put in carbon, and you also put in lime. And then, of course, into the furnace, you blast oxygen into it. And what happens is you generate liquid iron, and you also get stuff floating on the top. The stuff floating on the top is known as slag. Okay, and slag is typically calcium and magnesium silicates. So we use slag to make cement, for instance. And then we draw off the iron, and we used to draw it off and to put it into bars like so. Like, have you ever seen old school movies when they make swords or something like that? So look at these bars, like I guess maybe old school now. You've seen Lord of the Rings and the two towers. That's how they make iron to make the orc weapons. That would be a blast furnace. And a lot of times this product, it was actually called pig iron, because in the Industrial Revolution, we had farmers going from the farm to the factory, and they thought that these bars of iron being formed were like a mama pig with baby pigs suckling on the mama. And so that's where the term pig iron came from. We don't use that really much anymore, but maybe you've heard that before. Pig iron is pure iron. And we make all metals this way, with the exception of gold and platinum and some of the rare ones like rhodium. So gold we can just find as the material. We can also do some destructive things like mix mercury in rocks or mix cyanide in rocks. Aluminum is another one. We use electricity to make aluminum. But basically all the other metals, copper, zinc, lead, all of them are pretty much made the same way, and titanium as well. So this is how we make them, is by this process. It's a little bit of chemistry and society. And why am I telling you these things? Because students, the material is more important if we actually see the practical application for it, is what I found. The other thing is, so look at the amounts. 30 kilograms of carbon, 90 kilograms of titanium dioxide. This is something called a pilot plant. So let me think of something else. For instance, think about cookies. So when you make cookies at home, you make them you can buy the chocolate chips, and there's a recipe on the back. They say, take a bowl, throw in flour, sugar, butter, chocolate chips, mix it together, put it in the oven. Is that how they make cookies in a factory? And the answer is no. You have this big machine that churns everything together, and then it probably has this extrusion machine that plops out a certain amount, and then there's this conveyor belt that turns the batter over these heaters. It's probably like a infrared heater, and then out the back end, there's a conveyor belt, and then the cookies drop and they're sorted and they're put into boxes and shipped out. So that's how a factory does it. So if you want to change your recipe, say I want to make mint chocolate chip cookies now instead of regular chocolate chip cookies, and I want to make it with almond flour instead of wheat flour. So the problem is so you can make the recipe in a kitchen lab or whatever, and you can perfect the recipe where you like it. Now you got to scale up. You go from like making 20 cookies to making 200,000 cookies. And you want to optimize the process. So meaning you want to put out as many cookies out of your factory as you can in a small amount of period, because that's how you make money. Problem is, if you heat it too long, you burn the cookies. Or say you don't put enough pressure on the back of the extruder, cookies are too big or too small. So you need to have something in between. You have to have something in between the kitchen and your cookie machine, somewhere in between, and that's called a pilot plant. And a pilot plant is where you perfect the process, you make lots of mistakes, you burn lots of cookies. Difference is when you burn cookies, working with 30 kilograms of cookies is better than working with 30,000 kilograms of cookies. So you make the process as good as you can in the pilot plant, then you scale it up to the factory, and then you still make mistakes, but your mistakes are not going to be as dire as if you started off from the lab going to the scale to all the way to the factory. So that's how we make stuff. And so another thing, instead of cookies, think about the COVID drugs I sent you guys out, right? So once they get approved, if they get approved in the stage 3 trials, we got to figure out how to make, 1 billion doses of them. And so they're going to go through the same process. They're going to have to do a pilot plant and then do a scale up. So it's going to take time, of course. But anyways, back to this pilot plant. And I guess another thing with ore, if I go to Michigan and I dig up iron ore, is that going to be pure iron oxide? And the answer is no. There's going to be twigs in it. There's going to be calcium, magnesium, silicate impurities, that kind of stuff. Impurities in it. We don't have a pure product. We don't have a pure reactant. The carbon is not going to be pure carbon either. So that's the reason why these numbers are a little off. But let's go ahead and do this one. So we're going to have, this problem here, we have 28.6 kilograms of carbon reacts with 88.2 kilograms of titanium dioxide, and we generate 42.8 kilograms of titanium. So how do we solve this problem? So 28.6 kilogram carbon. So same thing. Oh, actually, I should 1,000 grams per kilogram. Mole carbon to 12.01 grams carbon. I can be 12. I know I'm just, let's see here, what's next? Then we have mole titanium to 2 moles carbon, and then 47.87 grams titanium per mole titanium, and then kilogram to 1,000 grams. And so in the spirit of the previous problem, we explain each step. So 28.6, that's given. Converting to grams. So periodic table, mole carbon is 12 grams of carbon. Then from the balanced equation, 1 mole titanium to 2 moles carbon. And then I put this on the side here. I actually don't have this memorized. I had that as a prompt in my lecture. 47.87 grams of titanium per mole. It's not, I don't know, Ki, that's titanium. Titanium. That's the atomic mass of titanium, and then we convert back to kilograms. So is that good for everyone? Same thing for the ore. 88.2 kilogram titanium dioxide, 1,000 gram to kilogram, mole TiO2 to 79.87 grams titanium dioxide times mole TiO2 to mole titanium, and then we get 47.87 grams titanium to mole titanium, then kilogram to 1,000 grams. Okay, let me see if I can cheat if this is already in the book. Although the book tends to do moles. I blew past it. Okay. This one is 52.9 kilograms. And let me see if I can shoot this way. As long as my cell phone cooperates with me, which it's not. Okay. 1, 9, 1 times 7. And doing this one, we get 57.0 kilograms titanium. Okay. So doing this one here, we look at the reactants, and if we start with carbon, we should get 57 kilograms. And if we start with titanium dioxide, we get 52.9 kilograms. And which one is the limiting reagent? It's this one, right? We picked the lower number. And now oops, sorry for the spin, sorry the barrel roll there. So next thing is we do the percent yield. I guess I didn't, the percent yield, I put the equation here. The percent yield is the actual yield divided by the theoretical yield times 100. So our actual yield is 42.8. Our theoretical yield is 52.9. We should get that, and we multiply it by 100%. And we get 80.9%. Okay, so let me go over a couple things. So the confusion of students, they usually ask, why don't I have 100%? And the reason is because of impurities and also just issues with the process. So you're making this thing in your mini blast furnace, and you're probably getting some stuff sticking to the walls. So things like that, and then, or maybe you're just not getting enough oxygen, maybe you're not putting it long enough. Not all of the titanium dioxide will react. That's another issue. You don't have a complete reaction. That's the reason why we don't have 100%. Can you actually have over 100%? And the answer is yes. Sometimes you get over 100%. You'll find this in lab. And usually happens because you don't dry your sample properly. So if you don't dry your sample, you'll get extra mass. So that's an experimental error, actually. So, but usually you get less. And actually 80%, that's a pretty good yield. And the other thing to note with this, if I were the plant manager and this was the chemist / engineer that did this, I would give that person a big pat on the back and try to give that person a raise. Because if you look at this, you have two reactants. You've got ore and you've got carbon. Carbon's cheap. Okay, we put it in our pencils, right? The ore is going to be more expensive. And so the person that designed this added a little extra carbon, the cheap stuff, but not too much. It's not a whole bunch more. We're talking about 53 versus 57. So we certainly have the cheap stuff in excess, but it's not too much of excess, but it's good to have the cheap stuff in excess because we're trying to push out as much product as we can. So this is a really smartly done process. So good job for the chemists and or engineers that did this. Okay, but so the new things, of course, we have old things and new things. The old thing, that we did was the theoretical yield. So we figured out this theoretical yield. The new thing is the actual yield. So we have or I should say the percent yield. The actual yield, this is given to you. Or if you're doing it in a lab, you measure it yourself. This is how much product I have. I got 42.8. I should have gotten 52.9. And the ratio times 100 is 80.9%. So that's the new step there. So how are we doing? Anybody have any questions? Do you want me to go over anything again?
So the theoretical yield and the limiting reactant are like the same, but when we do the test, if you want us to have it in that format, like the kilograms, for the limiting reactant, or you want the one on the
What do you mean? I don't quite. What do you mean the one on the left?
The 8.2.
I mean, honestly, it doesn't matter.
Like it'll stay.
Yeah. I'm just putting this is just the units. And also notice a couple things that the kilograms, these two steps, they cancel out. So you don't even have to put them in your calculator because you multiply by 1,000, you divide by 1,000. So, which actually brings me to another side point. If you see the word mole, it means gram mole. You might see a few times, you'll see something called a kilogram mole or a pound mole. And what is a pound mole? A pound mole is when you take the bottom end of the periodic table and you divide it by the pound. So a pound mole of carbon is 12.01 pounds of carbon. And a kilogram mole of carbon is 12.01 kilograms of carbon. So, and the mole is also the gram mole, but we almost always just ignore the gram and say mole. So if you see those units in the future, that's what they mean. Typically, though, we don't use that so much here. They do that in industry. So if you go work in industry, you'll see pound mole and kilogram mole, but you probably won't see that. You're not going to see that in academia because everything we do is in grams, and we don't say gram mole, we just say mole. So if you see gram mole, it means mole. Kilogram moles, it just means a kilomole, and a pound mole, it's whatever, kilomole divided by 2.2. So it's weird unit. I hate that unit actually. Anyways, other questions? Nope. Okay. I spent too much time talking. All right. 150 grams oxygen and 850 grams hydrogen react to make 50 grams water. What is the percent yield? And from last time, we had 100 grams of oxygen make 112.5 grams of water. So tell me, what is the limiting reagent? What do you think? Is it oxygen or is it hydrogen? Oxygen is the limiting reagent. And we just did this problem here and we found we got 112.5. And so if you have 50 grams, this is going to be 56.25 grams water. So and this is going to be the theoretical yield, and then this one is the actual yield. So our percent yield is going to be 50 over 56.25, I know, but times 100%. So what is that? Okay. So, well, people are still writing. Okay, take your time. And I know I've done some creative rounding for these problems. What's that?
Oh, sarcasm.
I think that was truthful. I think I did do some creative rounding. I mean, it's certainly not going to 2 sig. I guess it's not right for 2 sig figs.
I thought you were saying like coming up with the problems.
Oh yeah, I did. Yeah. Yeah, I wrote those myself. This one I tried to make it's obvious which one's the limiting reagent. I also just made it half of the other problem so that way you didn't have to do the math again. If you're wondering what I'm doing, Zoomers, I'm staring at people working on their calculator and look at their notes. When people stop writing, that's when I think they're done. Is that hard for you guys and the Zoomers to follow along, or is it just, truth be told, when I go to a Zoom meeting, I'm usually doing something else. I mean, I love doing my laundry during Zoom meetings, for instance. How many of you guys are doing your laundry? I guess you don't have to answer that question, never mind. Go to chemistry class, get clean clothes.
I was making food in the beginning of class, but now I'm not.
Oh, I didn't hear you, that's it. Well, don't worry about it. Okay, so how many people think A, 100%? I think B, 90. Okay, so we got half the class. Oh, we got more. Okay, I just wasn't looking hard enough. Yeah, B, 90 is the right answer. It's 89%, so that is the right answer. I forgot to talk about this, but if you look at this problem here, one of the things to note when you do these problems is to try and eliminate answers. So we're going back to the previous chem quiz. When you have 100 grams of oxygen, 100 grams of hydrogen, answer D here is 900 grams. If you have 200 grams of product, if you have 200 grams of reactant, you can only have 200 grams of product. So if you have more than 200 grams of product, you know that answer is wrong right away. So D's out. And C is very unlikely. You can almost just guess that's wrong too. It could happen, but it's unlikely to happen. And especially with numbers like 100 to 100 grams. So really your answers are A or B, your choices there. And you can kind of see that. So water though, you're gonna gain in mass. So if you have either oxygen or the hydrogen, the product is going to gain in mass. And if you're limited by one, the product is going to be slightly more massive than whatever your lowest amount is. So you can kind of logic your way through to B anyways. So, and if you solve problems that way, that's fine. You can figure out answers just by logic. So don't turn off your logic brains when you're taking tests. So especially for like the GRE or MCATs. So we got 6 minutes left. Does anybody have any questions about anything? I might do 1 or 2 problems then. And I'll do the ones that are from this chapter. You can see I put a bunch of them here. Okay. So oh shoot, maybe I I know Zoomers, you can't see it, or you can still see my iPad, but I had people in the class. This is one here. So this is going to be, what number is this? Huh. Oh, did I put in? Oh, it's 4.13. 4.13. So it's asking for, you have SO2 plus O2 plus water yields H2SO4. So the word problem went like this. Sulfuric acid, H2SO4, is a component of acid rain that forms when gaseous sulfur dioxide pollutant reacts with gaseous oxygen and liquid water to form aqueous sulfuric acid. So you need to balance this. And you have to look then to the ratios. So first of all, the ratio of sulfur to sulfur, it's going to be 1 to 1 here. So your SO2, for every unit of SO2, you're going to have 1 unit of SO4, H2SO4. And then also same thing for water. So you have H2 here, and you have 2 hydrogens there. So each unit of water, you're going to have 1 unit of sulfuric acid. And now you count up the oxygens. And so on this side of the equation, so for the oxygens, you have 2 plus 2 plus 1, and then you have 4 over here. So how are you going to do this? Well, if you notice, well, first thing you can do, I mean, I can kind of see the answer already. You multiply this by 2, and now you look at the oxygen balance. So multiplying the sulfurs and the waters by 2, and doing so now you have 8 here, you have 4 here, and you have 2 here, right? So actually then now written there actually does all sum up, where here you have not including the oxygen there. I guess this is kind of a hard problem using the logic and balancing. So, and now, like I said, it is balanced. But in solving this problem, you look to see the ratios. So in my mind, as I solve this, I link the sulfur, the water, and the sulfuric acid as set ratios. So because you can see there's 1 sulfur in the SO2, 1 sulfur in the H2SO4, there's 2 hydrogens in the water, 2 hydrogens in the SO4, and the hydrogens are only found in the water on the left and in the H2SO4 on the right, and the sulfur is only found in the sulfur dioxide on the left and the H2SO4 on the right. So the variable now becomes the O2. So, right now we have the wrong ratio. So what do? We start looking at, and it's pretty easy because we're having odd numbers. So you have to multiply by 2, and then multiplying the set ratios that we have. Now we've multiplied these by 2. Now we have to look to see the missing oxygen. And actually it finds out that 1 missing oxygen is one missing O2 is all we needed. So actually just multiplying by 2 balanced it that way. So that's my explanation. That's that logic to solve that equation. Does that make sense? Or some of you guys are looking worried? No? And that's my shut up alarm. Okay. So class is over. I will stop recording. Does anybody want something to, I'm going to